This presentation will mainly focus on representing the natural numbers n including 0 in a discrete binary two-dimensional form by radial combinations that can be extended to 3D. No formal proofs will be presented since this only is an overview. The proofs are, however, mostly very simple induction proofs. Some properties. The coordinate system is based on bounded areas rather than points. The system can wander by combining binary strings. Radial combinations can represent truth tables. The coordinate system can be converted to a Cartesian coordinate system. The derivative of a binary string representing a path can easily be calculated. The normal to a radial combination can be found by adding a 1 to the second most significant bit in a binary string. The reverse path given by a set of radial combinations can be found by flipping the most significant bit. An inner area-based coordinate system is represented. A coordinate system can be nested within another coordinate system. There is a potential to let the inner coordinate system be used in multiple ways since each compartment is an area. Let's start by drawing a diagonal of length 2r in a quadrant. Extend the diagonal with r on both sides. Draw an octagon with a diagonal of length 4r. Draw lines from the corners of the quadrant to the closest corner on the octagon. Draw an 16gon with a diagonal of length 6r. Draw lines from the octagon's corners to the closest corners on the 16gon. The procedure can be continued by creating a 32gon, 64gon, etc. We denote areas between n-gons as shells. Below is a grid with 4 shells. The first shell will contain 2 compartments, the second shell 4 compartments, the third shell 8 compartments, and so on. Hence the nth shell will contain 2 n compartments. We denote arrows that either point to or away from the center as radial combinations. We can achieve a corresponding compartmentalization using circles instead by just letting the corners in each shell define a circle and then remove the corresponding n-gon. Below is another way to represent the same system, but such a representation gets very compact and it's harder to visually represent the different compartments, so we avoid this approach for the time being. Let's name the compartments in the inner shell 0 and 1. Let's name the compartments in the next shell 0 and 1 alternating in an anti-clockwise manner. Let's continue this process for the rest of the shells, as the animation below show. A radial combination from one compartment in the center to an arbitrary compartment will have an unique address. The radial combination below gives the compartment in the fourth shell the unique address 0010. Let the inner shell represent the number 2 to the power of n if there's a 1 in that compartment and 0 if the compartment is occupied by a 0. Let the next shell represent the number 2 to the power of n minus 1 if there's a 1 in that compartment and 0 if the compartment is occupied by a 0, and so on. Binary strings can represent natural numbers n if we draw radial combinations from the inner shell to the outer shell. All natural numbers n ranging from 0 to 2 to the power of n-1 can then be represented by radial combinations. Integers z can be represented by finding the 2's complement by adding a 1 to the first complement. But we will focus on the natural numbers n in this presentation. You can find a 180-degree representation to a given radial combination by flipping the most significant bit in a binary string. Finding the normal is almost as simple, you just add a 1 to the second most significant bit. To find a radial combination corresponding to a 45-degree rotation, you add a 1 to the third most significant bit, and so on. An interesting symmetry is the fact that a binary string's complement can be found using the polarity line as a mirror line similar to the complex conjugate. The 2's complement can be found by adding a 1 to the least significant bit to the complement. A coordinate system based on radial combinations representing the natural numbers has many similarities with a polar coordinate system in the way it handles rotation, but the key difference is that the polar system uses real numbers to represent the direction of an object and is hence a continuous system. A coordinate system based on natural numbers can only describe discrete steps. This is of course a limitation in the sense that an angle in a polar coordinate system will be more exact. But an angle can be arbitrarily exact by extending the bound of the natural numbers by adding more shells to the grid. Let a radial combination be fixed. The grid can then rotate 4 steps around the center so that the radial combination is pointing at the blue dot. Another option is to rotate a given radial combination so that it points to the dot, keeping the polarity line fixed. A path can be described by letting the system wander based on a set of radial combinations in a vector-like manner. By flipping the most significant bit in every segment, the system can find its way back to where it started. A normal to a radial combination in a path can be found by adding 1 to the next most significant bit. You can then find the second normal by flipping the first normal's most significant bit. The path of a discrete wave can be achieved by letting radial combinations oscillating between 2 numbers stepwise as shown below. Damped oscillation can be achieved by following the path of descending ranges. The path of a star combining rotations and translations following an algorithm. You can get the same result if you want to keep constant polarity. A specific path to a compartment within the grid can be found by using inner radial combinations. A grid can be nested within another grid. The derivative of a radial combination can easily be found. Given two orthogonal grids, a position can be found in 3D by combining two radial combinations by first rotating the first grid aligning with a radial combination on the second grid, then rotate the RC into position on the second grid. Given the two radial combinations S10011, 00101, we first rotate the vertical grid so it align with 10011 on the horizontal grid. Then rotate the arrow on the vertical grid so it align with 00101. To find the normal to a given RC R1, R2, we need to add a 1 to the second most significant bit to R2. So in the previous example 10011, 00101, we add 01000 to 00101, since adding a 1 to the second most significant bit equals a 90-degree rotation. 00101 plus 01000 equals 01101, so the RC for the normal will be 10,011, 01101. To find the opposite RC R1, R2, we need to add a 1 to the most significant bit to R2. So if RC's position is 10,011, 00101, we add 10,000 to 00101, since adding a 1 to the most significant bit equals a 180-degree rotation. 00101 plus 10,000 is equal to 10,101. So the RC for the opposite direction will be 10,011. 10101. We can convert a position P where the absolute value of P is 1 given by two radial combinations to a Cartesian coordinate system following the steps below that are almost identical to the procedure, converting spherical coordinates to Cartesian coordinates. An example using the same RC constructed by 10011, 00101. The height z can be found given that the projection of P onto the xy plane form a right triangle. The base b is then given by b equals cos phi equals cos 62.12500.468. We can then add up the angles represented by RC equals 10,011 on the horizontal plane. And find the x and y coordinates. Hence x, y, z is minus 0.361, minus 0.297, 0.887. The grid can wander in 3D space as well. The path back can be found by adding 1 to the most significant bit to R2 as shown below. Let two locked grids be orthogonal and two RCs rotate coplanar within each grid, and let a third RC be fixed, the red arrow in the video below. And let the system move one step guided by the fixed RC after one rotational cycle. This will result in two waves perpendicular to each other and in phase. The rotation of the two radial combinations can be arranged so they are complement to each other. Let's visualize this in a less cluttered way by first hiding half of each grid. Each step in the horizontal grid has a complement in the form of a step in the vertical grid. The rotation for each arrow will be 360 degree, hence 720 degree in total. A radial combination R3, red path, can be formed by combining the two complementary radial combinations R1 and R2. R1 and R2 will rotate 720 degrees together, while the combination R3 rotate 360 degrees. Let's remove the grids to illustrate this less cluttered. A grid can also represent truth tables. The complementary radial combinations will describe the NaN truth value. A truth table can also be represented both by inward and outward arrows and have starting and ending point in different shells. A Boolean function can also wander around. A Turing machine that accepts even palindromes over the alphabet sigma equals A, B. Truth tables and internal processes inside a grid can hook up to other grids. Processes can be nested. We can make a variant of Conway's game of life by using square binary grids implementing Conway's set of rules. Truth tables can be represented with radial combinations within the grids that might respond to what's happening in surrounding squares and let the internal state of one newborn cell mutate, depending on the internal state of its neighbors. A blinker. A glider. The grid can also internally follow the rules of Conway's game of life. An AND function with an internal blinker. An interesting property is that leaving the outer shell's compartments blank will isolate the oscillator, but the state will alter if the grid come in contact with another grid. The blank third shell isolates the second and inner shell. Two oscillators can coexist in the same grid. The inner oscillator is shielded from the outer oscillator by the blank compartments in the third shell, and the outer oscillator is shielded from the environment by the blank compartment in the outermost shell. Blocks can form complex nested blinkers, etc.